So today I'm going to be talking about, actually pairs well with Dr. Madabushi's talk as well, an application of artificial intelligence or machine learning to look at prostate cancer margins and see if we can gather some insights that are going to be beneficial for focal therapy planning. Here are my disclosures. So artificial intelligence has got kind of a bad rap or a good rap, depending on what news you read, but essentially AI is algorithms that mimic cognitive functions of humans. We interact with these algorithms every single day without concern. Spam filtering, search, dictation, all of your fraud detection in your banking is governed by artificial intelligence. The key with AI is that it requires a lot of data. We're talking about billions, hundreds of millions of data points. In medicine, we're typically limited with the number of data sets that we have. So other techniques, could be adopted. But right now, there's a lot of interest in, deep learning. What I'm going to be talking about today, is a subclass of machine learning. We're going to be using very simple algorithms because of our data set limitations. So AI or ML in urology has been used many times. This is a good description of how these algorithms work. This is from a paper in Radiology in 2018. Essentially, you're taking an image, you're normalizing it, you're co-registering it with your existing data sets, and then you're extracting some sort of information or features. And these features, in the case of deep learning, could be sort of unsupervised, or it could be supervised based on your domain-specific expertise. So in this case, using composition of the texture, using radiomic features like Dr. Matabushi talked about before, and applying some sort of classification algorithm or way to detect cancer, not cancer, or whatever your objective is. The challenge with AI and ML is that, and urology is that typically we've been using MRI alone to create these algorithms. And in this study, 316 patients were used to develop a algorithm to detect presence of prostate cancer. Turns out that ADC alone outperformed any sophisticated ML algorithm in this paper. So this is where the state of the art is in terms of how we can use AI and ML in urology. Relevant to focal therapy is the goal of treating clinically significant disease while sparing healthy tissue and critical structures. And so this concept of margin becomes very important when deciding what sort of focal therapy strategy to perform, whether it's a true focal with a uniform margin, a quadrant-based approach, hemigland approach, or a hockey stick, 2 quadrants at half quadrant and then, half the prostate in the quadrant. But we know that MRI alone, from the work that's been presented today and before, is insufficient in estimating the true tumor burden in the prostate. MRI underestimates the total tumor burden by up to a centimeter, and in some cases, 15 millimeters. There's work that's published from our institution in 2017 that says that the average margin is 11 millimeters. That means that 50% success rate at 11 millimeters. And so we know that also from other work that's published by Dr. Ukimura's group that biopsy pathology has higher correlation with final pathology than MRI alone, and our work confirms this. So we thought, why not use targeted biopsy information to improve our prediction of prostate cancer margins? And so we developed work built off of the NIH's work on prostate-specific molds to carefully co-register whole gland or whole mount prostate with MRI, so we can characterize the true tumor with the region of interest. And because the MRI is co-registered with targeted biopsy, we can map the biopsy core all the way to the final pathology. In our study, we looked at 124 patients with whole mount prostatectomy. Most of these patients were GG1 and GG2 and 3. We then excluded patients with Gleason pattern 5 and patients that would be obviously ineligible for focal therapy with gross bilateral disease. We then created virtual biopsies. We did this because we wanted to eliminate the potential problems of an unknown co-registration error, segmentation error, deformation, warping, and then applied sort of modeled errors and virtually sampled these prostates multiple times. So we modeled needle deflection errors and image registration errors, and then virtually sampled a targeted biopsy plan of 12 cores plus 3 cores per PIRADS grade 3 or higher target. We repeated the simulation for each prostate 50 times and then balanced the positive areas with negative areas. So we had a balanced data set for training, which resulted in about 3,078 targeted biopsy virtual procedures, which is about 3.2 million image patches that we can use for true machine learning. We then extracted some custom features based on prior work that we had performed, seeing that the distance to a positive core, distance to the negative core, distance to the region of interest, all of these features are very useful in terms of predicting positive versus negative areas of cancer. We also looked at texture information on the MRI itself. We then used a technique which has been used for decades called support vector machine, and we used this very simple technique because we wanted to see what the performance of using this new type of information without consideration of a complicated machine learning model. So in a support vector machine, the objective is to maximize the separation between your two or multiple classes. And so the idea is to try to find a separable line that maximizes that margin. And then we used a derivation of this called support vector regression to then get a 0 to 1 output. So then we can apply some sort of probability map or create some sort of custom threshold to determine areas that are probable of cancer presence versus non-probable. Here's an example of what our probability map looks like. This data was in the lower right-hand corner is sort of our risk map for cancer presence, and this was done blinded to the whole mount data. So in green is the MRI visible lesion. The white area was our probability map, and you can see low to high, black to white, and red is on the T2-weighted MRI is the true cancer presence. And so with this, we performed this for 114 patients. We did 5-fold cross-validation, and then we compared the results to two strategies, the hemigland approach as well as a uniform margin approach. And we found significantly increased sensitivity, specificity, and accuracy in detection. We then looked at what is the implication for focal therapy planning, because at the end of the day, an ROC curve is nice, but what does that mean to clinicians? So then we looked at treatment success rates. If we applied a threshold on a uniform threshold on our classifier output, could we detect all of the cancer in a certain prostate? And comparing that to hemiablation and uniform margins, we outperformed in this data set the treatment success rate. Now, the caveat is that this is a retrospective study. Obviously, it's only based on 114 patients, but we are in process of applying a large targeted biopsy data set, about 60,000 biopsy cores from real patients and a deep learning model to validate this more thoroughly. We also looked at the impact of what the threshold was on the margin. So we came up with sort of 3 different thresholds based on the probability or likelihood of cancer presence. And so we call them the conservative or medium or aggressive thresholds. And you can see in an example case the impact of the aggressive threshold in orange, medium in yellow, and conservative in green on the true cancer presence in purple. And our hope is to create some sort of slider output in our treatment planning so that the urologist can determine, for this patient, I want to be more aggressive. For this patient, I have high degree of confidence that it's localized to one area or another. We also applied this same type of approach to figuring out who would be eligible for focal therapy? This is a question that's been brought up at this meeting multiple times, the consensus criteria of who is eligible and who is not eligible. And we used what we call consensus criteria, which is, the maximum Gleason score sum, like the Gleason grade, also presence of bilaterality, and if the MRI target crosses the midline or not. And, this, you can debate on whether this is consensus or not, but we thought that it was the most conservative approach of who would be eligible and not eligible for focal therapy. We then compared that to a output from our machine learning model that looked at the margin from a particular patient and determined based on that margin whether the patient would be eligible or ineligible for henny gland ablation by whether it crosses the midline or not. And our classifier output outperformed, the sort of naive type of criteria in both accuracy, positive predictive value, and reduced the number of false negatives by half. And this is preliminary work. Obviously, there's more to be done, but we think that looking at the spatial characterization of the targeted biopsy with the MRI in a machine learning model can help all aspects of focal therapy planning. In conclusion, machine learning can help potentially improve treatment margins and improve treatment success rates. Targeted biopsy information yields important complementary information to MRI. However, this needs to be further validated. We're currently working on a deep learning model with a larger multi-institutional data set. We're applying this to both eligibility and risk stratification, correlating our output with treatment outcomes. And we're also testing this prospectively in several clinical trials using laser ablation. I'd like to thank my colleagues from UCLA and some of our collaborators from Cornell and Stanford. Thank you.